My name is Aaron Saxton. I'm the data scientist, or one of the data scientists in the Blue Waters project office. The past year and a half or so, I've been working a lot with studying distributed training and how people can run their machine learning algorithms on large systems like Blue Waters. Since there's not much life left in Blue Waters, at least for this audience, this is more of the conceptual talk about how you do all this kind of thing. So to get started, I know it's a little bit pedantic, but statistics review. Let's see. There we go. So all of this stuff really is curve fitting. So I'm going to take the easiest curve fitting idea, just matching a linear model to some cloud of data, just some randomly generated data there. The thing that we teach in a college algebra course or an early math course is least squared method. Okay, so this is a good model to have in your head for intuition. Our data set is xi, yi, so those are all these blue little points through here. So x, y, okay. So usually data sets are such that for some reason the output value is relatively hard to measure. Things like large image data sets and getting it tagged, right? ImageNet is the big effort there to have graduate students go through and say, this is a cat, this is a dog, this is a chair. So that took lots of work to get that. So just a reminder, the error, okay, so to do least square method, we need to define what our error is. In this case, it's just an L2 norm between our proposed linear model and the cloud of data. So, right, this R here is this big long sum over all the training data points. And so I bring this up because this sum is what we're going to take advantage of later. Most error functions, all error functions, will be some linear combination of something, and if it's not, you can usually take a log and make it that way. So we want to minimize R with respect to M and B. M and B are the free parameters here. College algebra, this is, or I guess Calc 1 maybe. You take the partial with respect to M, partial with respect to B, set them equal to 0, and this is just a simple linear system. Great. So that's a simple linear system. However, most models we care about are nonlinear. So this method here, we will have to use something heavier. Okay, so other models, just quadratic model, arbitrary polynomial model, exponential, and logistic. All of these, so this has 3 parameters that you would have to do that optimization over. This has whatever degree of polynomial you want, parameters you'd have to optimize over. This is 2, and this is 2 again. The choice of your model, you still have the typical ideas of underfitting, overfitting, and something appropriate. Right, underfitting is your model just doesn't quite have the capacity, doesn't have the degrees of freedom to encode whatever pattern you're trying to capture. Our human eye says that, oh, and with the data available says that, oh, this is probably quadratic. But if you used a model with too many degrees of freedom, it's easy to train crazy things going on here. The reality probably is not that the y value is way down here. The reality is that it's probably somewhere in here. Okay, so now we move forward to a little bit of Calc 3. So to search those parameter spaces to fit your model, this really is just gradient descent. There are other methods out there. Few of them have an opportunity for parallelism. Things like method of successive approximations and all that are very serial process. So the reason we're going to hammer on gradient descent is because of, do I write it here? Because our loss function is usually this big long sum, an opportunity for us to do parallelism. Okay, so our loss function, I use the letter R because some of the literature I read does that. So we do a gradient on our loss function with respect to each of the model parameters. So in the linear case, that was the m and b. In a polynomial, it's all the coefficients of the polynomial. I'll give you an example of a more complicated model neural network here in a second. So it's the partial with respect to the parameters of your model, the coefficients of your model. So when you take a partial of that, that gives, that's what this vector field that I plotted down in the 2D plane down here, that's what this output is. So at a particular point, let's say right here, the loss function, the height function of the loss is right here. Intuitively, we look at this and say, oh, if we want to minimize, we're going to travel here. Oh, we look at this little vector, it says to move to the left. So this vector here says to move to the left. Right, so you initialize with some set of parameters, take the gradient, and you move wherever. However, there are opportunities for local minima. So if for some reason you blindly chose your initial model weights to be somewhere here, you might get stuck if you didn't choose a good enough learning rate. There are methods out there that do dynamic learning rates. Adagrad are all ones that do variable learning rates to help avoid these kinds of situations. So even though I'm displaying this in 3 dimensions, other big problems is in higher dimensions, you often get a lot of cyclic behavior. So you can have a vector field in a higher dimension where you wind up spinning around and perhaps not finding the optimal you're interested in. Okay, so recall, loss depends on data, right? This R depends on the fixed amount of training data you put in this. So if you chose a different training set, this manifold here possibly looks very different. Okay. So that was just a slide so I could blow this up a little bit there. Okay. Okay, so it depends on the data you put in here. So we're going to, however, we're going to kind of throw that out. In that what we do, most methods today use stochastic gradient descent. So intuitively, you might say, oh, I want all the possible training data I can get my hands on. I'm going to go stick it all into this big long sum. Who cares if it takes more memory? I buy bigger machines and squeeze it all in there, whatever. Well, with the size of data we're working with right now, trying to squeeze all of that data into this loss function all at once becomes prohibitive. It also turns out that it becomes resource prohibitive. It also turns out that that doesn't necessarily give you the best direction to go into. Remember, if you choose a different set of data, this manifold is slightly different. And if you go dump a whole bunch in there, and you get this loss function, it doesn't necessarily tell you the best way to go. You might have to. It might give you all these weird little troughs in here that you wander around until you actually find the spot, your optimal. So it turns out that stochastic gradient descent often gives you better convergence rates. And stochastic gradient descent, you choose one example. You say, all right, here's my big set of training set. Take one example out of it. Compute this loss with only one term here. So sum over only one. Compute the gradient and go update. Put that training example to the side. Now go grab another one and do it again. It turns out that because computing the loss function takes up less resources and the computation to do that is faster, you wind up updating your model weights faster and more frequently. So over the same amount of time, instead of following the institution of, oh, let's try to jam all this training data in there and just try and go in the best direction, it's not necessarily the best direction, and it takes you a long time to get every update of your model. So stochastic gradient descent is about taking, the pure version of it is taking one example and doing it over and over and over again. Unfortunately, stochastic gradient descent is a very serial process. You have a set of 1,000, 10,000, a million, whatever training examples. You got to start with the first one. Compute, move, grab the second one. Compute, move, grab, and so forth. Let's see, where does learning rate choose next? A shuffle training set, good. Stochastic gradient descent with mini batches sort of splits the difference. So instead of just taking a single example, or instead of taking your entire set, you take mini batches. You go take your whole training set, you shuffle it all up, and you take mini batches of each piece. Stochastic gradient descent with mini batches. So your sum here, your sum of your loss function, will only be over, say, 16 examples or so. So that's still relatively fast to load into memory, to compute this loss here, and to update your model. And there is a sweet spot there, depending on your how much memory resources you have, depending on how much memory and how complicated your function here and your loss function is. Let's see, how am I doing? Okay. So this stochastic gradient descent with a mini batch size, the particular size of your batch, it depends on the model and the data set you're training on. What is the optimal value? I typically start with anywhere from 8 to 16 with image data type things. Some of the other things we're doing, batch sizes of 256 wind up working also. Okay, so many training examples, some over many, but not all of them. Batch size or mini batch size, this gets ambiguous. Oh, right. So batch size or mini batch size, the nomenclature there gets a little bit ambiguous. The mini batches are our opportunity for parallelism, right? Pure stochastic gradient descent, you take one example and you have to walk through all of them. Since we now have a linear sum of a few of these things, what you wind up doing is giving an example to each of your workers, or maybe a couple of examples to each of your workers. You let them compute this loss here. Okay, actually, and then you let them compute this loss, and we'll talk about the more of the details in a second. Oh yeah, so stochastic gradient descent often outperforms traditional gradient descent. We want small batches typically because the opportunity to update your model is more important than trying to get the intuitive best gradient direction in terms of overall performance. Okay, so all right, now let's apply this to something that would be considered machine learning, neural networks. Neural networks have an activation function in them. Traditionally, a logistic S-type curve, a sinusoidal or an S-type curve is what you would want. Most of the classic theory considers this thing. So where you max out at, let's see, how did I plot this one? Where you max out at 1 and 0. There's a horizontal asymptote here and here. You can use arctan. It has a similar idea, pi over 2, negative pi over 2. It turns out that even though classic theory deals with more complicated functions, these take larger polynomial expansions to compute and whatnot. It turns out that this guy here is just as good as anything. In terms of, at the end of the day, the empirical evidence says that a rectified linear unit is just as good as anything else. Is that flickering bothering you guys? Okay. Yeah, I heard yes and no. Uh-oh. Okay, so now let's take that idea. So a neural network is, so the parameter is a function. Many inputs to many outputs. This is the formula for it. So your inputs are your x's. Your sigma here is one of those examples from back here. It's a nonlinear function that we apply to the transformation. This is just a linear transformation. This is why tensors are so popular. This room knows a lot more about tensors than TensorFlow takes into account. But nonetheless, everything, a lot of the heavy lifting is just vector matrix multiplies through here. but then it get a nonlinear function, pointwise nonlinear. The output of your linear transformation is pointwise applied to your nonlinear function, and that's what this hidden layer is. And then another a linear transformation tells you how things get split up into the outputs. So this is just some complicated function, multiple inputs, multiple outputs, and our task is to optimize that against some training data. Optimize the weights. Okay, so in order to explain the parallelism, or the details of the parallelism, let's just think of some faux model example. This happens to be a convolutional neural network. Here's a fully connected section. This is an example of what I just showed you. So maybe 6 inputs, or why did I say 6? Maybe 6 hidden layers. I have a 5 by 5. No. 6 inputs, 3 hidden layers, and then 2 outputs. Why? Why not? It's just a faux example. So trainable weight, each one of these layers, the convolutions have some trainable weights, and the fully connected layer has some trainable weights in there. Okay, so distributed training, data distributed. You take your model, you initialize it with some collection of weights, and you go copy it across all your workers, or you go copy it to be given across, in this case, across 4 different workers. So data is distributed, you take your model, you copy it, you spread it all out. You take your list of examples and you chop them up and then pass them out to each of the worker. Okay, in HPC, the best way to do this is with all reduced collectives, packages like Horovod and the Cray ML plugin, which are both on Blue Waters. This is what they do. The default out of the box, yes, this is what they do. PyTorch also by default has some MPI that's working, I think. It was at one point. Okay.
201 is probably breaks and things like that.
Okay. So Horovod, Cray ML plugin, and PyTorch all have features to do all reduced collectives. Tensorflow out of the box has this worker parameter server type idea, which I'll explain here in a second. That is not the way we want to do it in HPC. Okay, so what winds up happening is each one of your workers has a copy of the model. Each one of your workers was given a list of examples to crunch on. And so each one of your workers, say you have a batch size of 8. A total batch size of 8 means each worker is going to take 2 examples, push it through the model, compute a loss function, compute the gradient. Here we go. Yeah, cool. Compute the gradient, do an all reduce, pass the gradient around. Okay, so the all reduce, it basically sums everything up. So these collectives are nice because this worker broadcasts its value and then has some aggregation function, and it's just a sum. Has some aggregation function, and you get your gradient tote back. So everybody gets the same gradient total back. Everybody broadcasts their particular one, and gets their same, and then updates their model. And then they move on to the next 2 examples. So effectively, if each worker is working with 2 examples, effectively the batch size is 8. The mini batch size is 8. That's why in that previous slide I said, oh, this can become a point of confusion. Oh, but I set mini batch 3 or mini batch 4. Yeah, but your batch size is 256 because you got however many workers. So you're going to not converge as nicely, right? We want small batch sizes. Unfortunately, small batch sizes is not good for parallelism. Okay, so bad way to do it. I'm telling you about this just to, on HPC, avoid it like the plague. maybe someday people, well, whatever, just avoid it. So what winds up happening is one worker, or in my model here, two workers wind up being parameter servers. That means they keep the values of their particular of the aggregate values of the model. Maybe they have a big long model and they split half the parameters on one parameter server and the other half on the other, or maybe they just copy it for redundancy. You can configure it in either way, and so they serve those parameters out to the various workers. The various workers say, "Hey, I need some." The various workers say, "Hey, I need some data. Go take whatever examples off the top of the stack, crank it, and then pass back the gradient back to the parameter server where it gets aggregated." This is useful for an AC. So this approach is a very synchronous approach. Literature suggests that synchronous training is infinitely better than asynchronous training. This system was designed for more of an asynchronous idea. You have some parameter servers that manage, where's the model actually updated at, and then you have workers just grabbing data whenever they have the opportunity and cranking it through whatever version of the model they wound up getting at that particular time. The convergence properties of this are poor. The loss convergence. Okay, so that's what works. That's what we know how to do data distributed training of a machine learning model, for instance, a neural network or a convolutional neural network. What time do I have? When do we start?
You started a little bit late. You have
5 minutes? Oh, okay. Any quick questions? Okay. What doesn't work? So one thing that's coming up in the literature, and was it 2015? In my opinion, the image classification and image segmentation problem was basically solved. They're refining it. They're discovering new interesting things. So things like labeling your images, saying, "Oh, here's a person, here's a dog." Now we're worried more. Now that the big research is happening in a topic related to sequence modeling. Traditional sequence modeling were done with autoregressions, where the crux of it was computing all your backshift operators, and often you'd use an autocorrelation to try and determine what your backshift operators were, and you go train the weights on some data to say, "Oh, I have some input signal, and my model says, oh, this is how the next things can happen." Okay, so but that same idea works for semantic labeling. The quick red fox jumps over the lazy brown dog. I'm not an English major, so I hope I got all my parts of speech right. So article, adjective, noun, and so forth. So the input sequence would have been this list of words. The output sequence would have been this list of tags. So that's a sort of what's coming up in the literature as the next challenge to do here. But you can imagine if your experiment is doing some signal processing, maybe you want to fill in gaps in here. Oh, the guy I wanted to tell this to isn't here. Here I drew this picture, so you continue it out. Maybe you want to fill in gaps with errors and that kind of thing. This might be a technique to do that for more scientific applications. The technique is recurrent neural networks. This is the most generic version of all this. Turns out recurrent neural networks by themselves, unless your sequences of data are super sharp, aren't very useful out of the box. They have something called the vanishing gradient problem, which deep neural networks also have, but can be fixed. There are, so on top, so I'll explain this image here in a second. This is the basic idea, but modern things are things like LSTMs, long-term memory, or gated recurrent units are the more modern version of what I'm about to explain. So recurrent neural networks, just like neural networks, had this idea of you have your input data, you have a transformation, you have a nonlinear function, then you have another linear transformation after that. We've rearranged some of that. So here your input is down here, the X. Your output is your O. And so U, V, okay, so I'm just putting in this guy here. So U, V, and W, whoops, U, V, and W, and H are a weird formula. I mean, this diagram explains what that formula is, of how you transform your first token of your sequence to get your of your input sequence to get your first token of your output sequence. So what winds up happening is you have a trainable transformation. This could be a matrix or a vector-vector multiply. Trainable weights here. That gets hit on the X. Then again, a trainable H. An additional linear transformation is done. Trainable D, an additional linear transformation is done, and some type of softmax to decide what the actual classification of your output is here. So linear transformation, linear transformation, linear transformation, linear transformation. The thing that makes it a recurrent neural network, though, is this is called the hidden state. So U gets applied to X, H gets applied to UX, and then W gets applied to H, or it gets applied to HUX to decide what the next values of the hidden state are. So this hidden state evolves as it walks down its sequence. And the idea is the values of U, W, V, and H are all trained in such a way that your initial H are all trained in such a way that if you go and numerically tokenize the red, brown fox, these transformations would output a numerical equivalent of article, adjective, so on and so forth. Yeah. For training, there's a loss function, and then there's your actual training data up here. The reason I popped this image up here is if you have 1,000 token sequence, to train this, you have to go lay out all your inputs and all your outputs, and this is effectively a very deep, deep neural network where all your H's are different layers in that network. This thing, on any useful a recurrent neural network, this thing can't be hosted simultaneously in memory on a GPU or that kind of thing. So you do things like windowing and varying your sequence size, and you got to hop through tricks. My point is splitting up your batch data the way that the more traditional things were working, you just have to start being more clever. So the punchline is things like Cray ML plugin and Horavad basically won't work out of the box in this kind of way. You just have to be more clever about how you take your sequences and shrink them down in nice ways. All right, but this is, there's no good answer to the, whoops, oh, darn it. There's no good answer to that last piece at the moment. That's why I didn't go into too much detail, and that's why I'm just giving words of warning. If you want to noodle through it, talk to somebody like me or Rashab or anybody else in the Waters team. That's what I got. Any questions? Yes. Mm-hmm. The K4? I don't know what that is.
So it's basically when you split your train test,
Mm-hmm.
your training test into multiple splits.
Oh, okay. So I mean, you can do like 40, 60 and that kind of thing.
Not just the proportion, but you randomize the samples that you get.
Mm-hmm.
So you can keep doing it 80-20, but each time the 80 is different.
Right. So that would go back up to the manifold picture I have. It turns out machine learning algorithms like to find things that don't matter. So what you want to do is you want to make sure your training set does sample as much of reality as possible. But one way you can kind of try and force your optimization algorithm not to key off of dumb things like, border textures on your images or something like that, is to start splitting up your training set and only training on one and only training on another, and maybe do some type of democratic voting for which one to take out. No, that did not relate to it, but that is another opportunity for parallelism. The two that I didn't talk about is one that you just brought up. The other is hyperparameter optimization. That's a big task. So if you keep your model small, small-ish, you can also use HPC to do hyperparameter optimization. So split your model across everywhere with slightly different learning rates or batch sizes or number of hidden layers, and then at the end use some kind of democratic process to say, oh, this was the model with the best hyperparameters. So that would so that's what you would do in this. Take your training set and split it in 4 ways, and have each model have that training set go train itself on that, and then vote to see who wound up being the best model after everything is said and done. So that's another opportunity for parallelism. But no, that's not what I was talking about here. Yep. Anything else? Yeah.
You started off saying it's all based on statistics. And when you look at that, a linear fit to a straight line, a good model should miss about a third of the point based on random statistics.
Right.
Is there any similar measure here for these neural networks? How do you know whether you fit or overfit?
So nobody knows what the universal set is,